All right, let's jump right in. We're going to go on a little journey today from 2 dimensions to 3. We'll be looking at how the simple flat shapes you already know, squares, circles, triangles, can be stacked, folded, and even spun to build the entire 3D world that's all around us. So let's get into it.
I mean, really think about it for a second. It sounds kind of like magic, right? We start with something that's totally flat, something with just length and width, and then somehow we end up with something solid, something that actually takes up space. So how does that even happen? Well, believe it or not, it's way simpler than you'd think. Just look at this. A single sheet of paper is just a plane, right? But what happens when you stack another one on top, and another, and another? You're adding a whole new dimension, height. You're literally building upwards, and that collection of flat planes becomes a solid object. And that right there? That one idea is the key to understanding pretty much everything we're about to talk about.
Okay, so to talk about these 3D objects, we need a couple of core concepts. First up, surface area. The easiest way to think about this is like, it's the wrapping paper. It's how much paper you'd need to cover the entire outside of a gift. It's the object's skin. And then you've got volume. That's the stuffing inside the gift box. It's the actual space the object fills up. So one measures the outside, the other measures the inside. Simple as that. So where do we start? Well, let's start with the most fundamental 3D shape, kind of the building block of our world, the cuboid. Or, as you and I probably call it, a box.
Remember what we just saw with the paper? A cuboid is basically the exact same thing. It's what you get when you take a flat rectangle and just stack a bunch of identical copies of it until you reach a certain height. The area of that first rectangle, that's your base. And how many layers you add, well, that's your height.
And boom, just like that, you can see where the formula for its volume comes from. The area of that base is just length times breadth, right? Then you multiply that by the height, which is really just the number of layers you've stacked. So here's the big takeaway. Volume is simply the base area times the height.
Okay, so that's the inside taken care of. But what about the outside? The wrapping paper part. How do we measure that? Well, the easiest way is to just imagine deconstructing the box. If you could cut along some of the edges and lay it totally flat, you'd end up with a shape like this, which has a cool name. It's called a net.
And here's the brilliant part. By doing this, we're suddenly back in the 2D world we know and love. The surface area of that 3D box is just the total area of these 6 rectangles. You've got a top and a bottom, a front and a back, and 2 sides. You just figure out the area of each of those faces and add them all up.
All right, let's move on to our next shape and see how this idea builds. We've mastered stacking, but what happens if we try rolling? Because this is how we get a cylinder.
Now this is such a cool way to see it. If you take a flat piece of paper, a rectangle, and you just curve it around so the edges meet, boom, you've just formed the body of a cylinder. The height of the paper becomes the height of the cylinder, and the length of that paper, that becomes the distance around the circular base, its circumference.
So if you want to find the total surface area, you just add up the parts. You've got the area of that rectangle that makes the curvy body. Then all you need to do is add the area of the 2 circular lids, one for the top and one for the bottom. Body plus lids, that gives you the total.
And what about the volume? You guessed it. We go right back to that very first principle. Just like the cuboid was a stack of rectangles, a cylinder is nothing more than a stack of circles. You find the area of that circular base, that's pi times the radius squared, and you multiply it by the height. See, it's the exact same logic.
Okay, we've stacked and we've rolled. Now let's bring in a third, kind of more dynamic way of creating shapes, spinning. And this is where we get into some really elegant, beautiful forms, like cones and spheres.
Check this out. If you take a right-angled triangle, hold it by one of its straight edges, and just spin it around that axis really fast, its long slanted edge, the hypotenuse, traces out the shape of a cone in the air. It's a 3D object created entirely from the motion of a 2D shape. Pretty cool, right?
Now, the sphere. It's maybe the most perfect shape there is, and it has this truly beautiful way of showing us its surface area. Imagine you take a ball and you very carefully wrap it with string over and over until every single inch of its surface is covered. Now, hold on to that string, because now it's time for the big reveal. We unwind it. If you take that exact same length of string and you use it to fill in flat circles that have the same radius as the sphere did, you'll find something absolutely amazing. It doesn't fill 1 or 2 or even 3. It perfectly fills exactly 4 circles.
Isn't that wild? This is one of those mind-blowing, elegant truths in mathematics. It's not just close, it's not an approximation, it's an exact relationship. The surface area of any sphere is precisely 4 times the area of a circle with the same radius, and that gives us that famous formula, 4 pi r squared.
So, we've got all these formulas and these cool ways of thinking about shapes, but why does any of this matter? What's the point? Well, this isn't just theory locked away in a textbook. Understanding surface area and volume is absolutely essential for describing, building, and interacting with the world all around us.
I mean, think about it. Every single time you wrap a gift, you are intuitively solving a surface area problem. You're trying to figure out if you've got enough wrapping paper to cover all 6 faces of that box.
Or what if you're building something? Let's say tiling the inside of a water tank. To figure out how many tiles you need to go by, you have to calculate the surface area of the 5 faces you're going to cover. That's the bottom and the 4 walls. It can even be used for some pretty creative estimations. Get this, a corn cob is roughly the shape of a cone. So if you know about how many grains of corn fit in a square centimeter, you can use the formula for the curved surface area of a cone to get a surprisingly good guess of the total number of grains.
Ultimately, what all this shows is that these ideas that sound so abstract, surface area and volume, they have incredibly concrete real-world applications. They are the tools we use to plan, to build, and to make sense of the physical space we all live in.
So, I'll leave you with this little challenge. Look around your room, right now. Pick an object, a book, a can of soda, a ball, whatever. You now have the tools to describe its outer skin and the space it fills. Go on. What are you going to measure first?